The final type of circular motion we're going to look at is satellite motion. And the first thing we need to look at before we can get onto satellite motion is thinking about gravity and the forces that are in action in a system. So here I have a planet, mass 1, and here I have a satellite, mass 2. This isn't really drawn to scale because the planet is much, much bigger than the satellite. So Newton came up with an equation here, which is saying that the force acting on these objects is equal to G m1 m2 over r squared. And Newton's third law tells us in what direction this force is acting. So there's obviously a force on the satellite towards the planet here, which is the weight force, or the force due to gravity on the satellite. But Newton's third law will also tell us that the force on the planet is equal to this force, but in the opposite direction. So there's also this force here acting on the planet. Now, because the planet has so much mass compared to the satellite, this force causes an insignificant amount of acceleration here. But over here, this force acts towards the planet, so can provide a centripetal force, a force towards the center of the circle, in a scenario like this, where the satellite is in orbit around the planet. Now, in level 3 physics, we really only deal with simple orbits, circular orbits. In reality, other than satellites that we put up into space, most orbits are elliptical. So, how can we use this equation here? Oh, that reminds me, one thing. The weight force here, remember we always use F equals mg to work out the weight force of an object. Well, that actually comes directly from this equation here. G is the gravitational field strength, and what we can do is take out one of the m's here. So let's say it's the satellite's weight force. It's equal to all of this other stuff, G m1 over r squared. Okay, so this here, all of this stuff is equal to little g, which on Earth is 9.81 meters per second squared. But what you can do now with this equation, you can work, if you can get these values, like the mass of the Earth and the radius of the Earth, to as many decimal places of accuracy as you want. You can get a very, very accurate measurement of what G is. And that reminds me, big G. What's big G? Big G is the gravitational constant, universal gravitational constant, and big G will be given to you. Big G is equal to 6.67 times 10 to the negative 11, and here come the units, Newton meters squared per kg squared. So these laws that we have, or these equations that we use, they are developed, well, I guess they model reality, and sometimes the units that we put on things like mass and meters, sometimes they don't quite fit, and we need some sort of constant to make our equations work. And this is the gravitational, universal gravitational constant, which is required to make these things all come out as observation shows they do. Okay, so down here, if we have an object in orbit, in a circular orbit around another object, then again there must be some sort of centripetal force on this object, Fc. And in this case, so the object's going in at a certain velocity, like so, at a tangent to the circle, but there's this unbalanced force towards the center. And in this case, the force is provided by the force due to gravity. So here, because the object's really far away from the surface of the Earth, we can't just use little g to calculate its force due to gravity. We need to use Newton's equation up here, because this radius is so big. This little g only works when the radius you put in here is the radius of the Earth. Okay, so we only use little g to calculate the weight force on objects near the surface of the Earth, which is most scenarios. Until we get satellites, until we get out into space, then we need to use this equation up here, which is given to you. Okay, so what does that mean? Well, here the centripetal force is still equal to mv squared over r. So that's the centripetal force, but here the centripetal force is provided by the force due to gravity, which is equal to all of the stuff up here. So the radiuses we're looking at here are the same. So the radius of the circle that the object is travelling around is r, and the radius, which is the distance between the centre of masses of these two objects, is the same. This mass here is the mass of the object in circular motion. So that's it, mass 1. Oh, sorry, mass 2. From up here, it's the satellite mass, mass 2. Cool. So these two things are equal to one another. I might rewrite that down here. m2 v squared over r equals g m1 m2 over r squared. So you can see here we can simplify this equation a little bit. We can get rid of these masses. Now we can really only do this if mass 1 is much bigger than mass 2, which is the case in this scenario. Because if mass 1 is much greater than mass 2, then the centre of mass of the system is the centre of mass 1. If these were of similar mass, then the whole scenario becomes a lot more complicated, but you won't have to deal with that at level 3. Okay, so these two masses cancel out, and now we can rearrange this equation, and I'm going to rearrange it to make v the subject. So the first thing I do is take this r to the other side, and I get g m1 r over r squared, and that means this and this cancel out, and the velocity of this object is going to be equal to the square root of the universal gravitational constant times the mass of the planet divided by the radius. So this isn't given to you, but often you'll be asked to work out the velocity of the object. Which reminds me, the velocity of the object is always going to be equal to its displacement over time. Remember, there's no exceptions to our rules in physics. And a common way for this to work this out, this velocity of the object, is you might be given the time it takes to do a full orbit, which is called the time period. And the time period is time to do a full orbit, which means the time it takes for the object to travel around the circumference of the circle. So in place of displacement, if we put in 2 pi r, 2 pi r, which is the circumference of the circle, and divide that by the time period, capital T, this is often how you'll work out the velocity of the object. This isn't given to you, okay, so you need to remember the equation for the circumference of a circle. This equation up here, the velocity equation, is given to you. Great, so that's circular motion in a nutshell. I will try and do some practice problems now for you as well.